Look up at the night sky, and it feels completely still. For centuries, astronomers looked at those fixed points of light and reasonably concluded that the universe was a peaceful, eternal, and static expanse. But 13.7 billion years ago, there was no sky. There was only the singularity, a single point of infinite density and infinite temperature, where the entire future universe was compressed into zero volume. The Big Bang was the rapid expansion of space itself. In this animated grid, the dots representing matter move further apart because the space connecting them is stretching in every direction at once. That peaceful night sky hides a more chaotic reality. We are currently living inside the cooling aftermath of that continuous cosmic stretching. A fraction of a second after that expansion began, 10 to the negative 32 seconds, the universe was a chaotic, blistering soup. Quarks and anti-quarks constantly slammed into each other, annihilating upon impact and converting into flashes of pure energy. A tiny mathematical anomaly in this chaos provided all the raw physical material for the future. For every billion anti-quarks, there were 1,000,000,001 quarks, and those survivors built everything that exists today. By the 3-minute mark, the universe had expanded and cooled just enough for those surviving quarks to slow down and bind together, forming the first protons and neutrons. It took another 300,000 years for temperatures to drop enough for the next phase. This diagram shows free-floating protons capturing erratic electrons, locking them into stable orbits to form the first hydrogen and helium atoms. This massive drop in temperature converted raw, chaotic energy into the stable, transparent building blocks of all matter. That early atomic gas was not perfectly uniform. Tiny anomalies in density existed across the expanse, creating microscopic clumps in the drifting hydrogen and helium. Gravity exploited those denser pockets. It pulled in surrounding gas and dust, accumulating them into the colossal, turbulent structures we call nebulae. As these clouds compacted, the intense friction and gravitational pressure at their cores drove temperatures high enough to ignite nuclear fusion. These were the first stars. Without those initial imperfections in gas density, gravity would have had nothing to pull together, leaving the universe a cold, dark mist forever. 9 billion years later, a localized event in our galaxy began our specific origin story, the formation of the solar nebula. This was a flattened, rotating disk of gas and dust. As it orbited a blindingly bright young sun, the material began to cool and solidify. Within this cooling disk, a process called accretion took over. Cooling dust grains physically stuck together, forming the small, rocky bodies we call planetesimals. These planetesimals spent millions of years in a cycle of violent collisions. They fused together upon impact, accumulating enough mass to build solid protoplanets. Our Earth took shape through these high-velocity impacts, fusing the debris of a dying solar cloud into a solid planet. The early Earth was a volatile, liquid rock. Constant asteroid bombardment and immense gravitational pressure kept the planet in a superheated, molten state. Because the planet was liquid, gravity triggered a sorting process called differentiation. This cross-section shows a randomized mix of particles. Under gravity's pull, heavy elements like iron sank to form the central core. Lighter materials floated outward, eventually solidifying into the rocky crust. This gravitational sorting gave Earth its heavy iron core, the engine required to generate the magnetic fields that protect life from cosmic radiation. As asteroid impacts decreased, the Earth's surface finally cooled. The lighter floating material solidified into a hard rocky crust. While the surface hardened, the interior remained boiling. Continuous volcanic eruptions vented trapped water vapor, nitrogen, and carbon dioxide from the hot interior into the primitive sky, a process called degassing. When the atmosphere cooled, that volcanic water vapor condensed. It triggered millions of years of continuous torrential rain. This rain pooled into surface depressions and impact craters, creating the very first oceans. By 3.8 billion years ago, these oceans became the cradle for the first living organisms, which would eventually transform the planet through photosynthesis. Everything on Earth, the ground beneath us, the water in our oceans, and the molecules in our bodies, is the cooled, stabilized remnant of a 13.7 billion year thermodynamic chain reaction.